So the next lecture covers stuff from first few sections of chapter 4, and so in terms of exponential equation. And so have this equation. Population, world population, in terms of billions of people, given by 6e to the 0.012 t. Right? And so you got that in maybe the year 2000, we had 6 billion people. And so this will be in terms of from that year. And so I know how many people on the planet in the year 2050. Right? Well, 2050, that would be 50 years after the year 2000. So T is going to be 50, and so then the amount of people on the planet, so the population will be 6e to the 0.012 times 50, right? And so somewhere on your calculator you should have an E button, it'll be right above your natural log button. E is a number like pi, goes on forever and ever. And if you plug this in, you'll find out that this will give you that there will be 10.9 billion people on the planet in the year 2050. So exponential equation. So we have in terms of two types of equation. You have linear, and then you have exponential. And so if you graph those two, so to put those both on a graph, linear equation would then be something that goes like that. So linear equation really gains at the same amount each time frame. So either same gain or loss. An exponential equation, you now are looking in terms of rate. Right? And so you have the rate is the same, but the amount you add every time frame is changing because the base is getting larger and larger. Right? So linear equation grows by a constant amount. And then exponential grows at a constant rate. Are the two types talk about. So then in terms of given a chart, so given some items, x and f of x, again f of x is the same thing as saying y. And so if we have these numbers, 7, 12, 17, 22, and then we had another chart, and the same numbers. And so we have 2, 8, 24, and 64, right? Now when I look in terms of are they linear or are they exponential? Well, if I look in terms of this one, we see here that the difference is 5, here the difference is 5, here the difference is 5. So this one is linear. If I look in terms of this one, we see here that the difference is 6, here it is 16, and here it is 40, right? And so it's not growing at a constant amount. And so we're going to look at this one is going to be certain in terms of some type of an exponential thing going on here. Right? So we got in terms of two types, right? So a constant amount, and that one in terms of what's going on there with the rate. Well, in terms of our exponential equation, we're going to look at a basic one being y equals 2 to the x. That's our basic one. And so, for example, we'll pick some numbers. x from y. Do 0, 1, 2, and 3. So if x is 0, 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, and 2 to the third power is 8. And if we were to put that on a graph, so we got when x is 0, y is 1. When it's 1, it's 2. When it's 2, it's 4. And when it's 3, it's 8. Right? So we know going this way, my curve is looking like this. And then what happens when we go in the other direction? And so if this is minus 1, minus 2, minus 3, yeah. Again, minus exponent, that would be the same as 1 over 2 to the first, so this is 1/2. This would be 1 over 2 squared, so this is going to be 1/4. And this would be 1 over 2 cubed, and so this would be 1/8. And so when I go this way, we got that it's tailing off something like that. Right? So we got in terms of our quadratic, our exponential, and basically they're all going to look basically the same. So as long as b is greater than 1, they're all basically going to have the same kind of shape. Well, in terms of this graph, we can do things with it as far as changing the way it looks a little bit. And so, for example, if we graph y equals minus 2 to the x, and we ask, well, what does that do to my basic shape? Well, we said that 2 to the x will look something like this. And minus of 2 to the x, well, that just takes that graph and it's going to flip it. And so now it looks like that. So we just flip it about the x-axis. Right? Well, and then we go, well, what happens if I graph this one? Y equals 2 to the negative x. Well, it's going to take this shape and it's going to flip it this time about the y-axis. Right? So we can take our graph and we can flip it about the x, we can flip it about the y-axis. Right? Other things we can do with the shape is if I had an equation like this, y equals 2 to the x plus 3. Right? Well, what that is going to do, it's going to take the entire graph and it's going to move it up 3 units. Right? So the line that it didn't cross before was the x-axis, so now the new line that it will not cross is going to be at positive 3, and then we get the same shape, but just now 3 units higher. And then if I graph, y equals 2 to the x minus 3, let's just do that. If I do this one, 2 to the x minus 3, well, it would be the same shape, but it would just now be 3 units lower. And so we would have my asymptote minus here, and my graph would now look like that. Right? So we can take a graph and we can move it up and down. Right? Well, other things we can do with our graph then is in terms of left and right. And so if I have y equals 2 to the x plus 4, right? And I want to know, well, what does that do to my graph? Well, we know that when this number is 0, the exponent is 0, my value is going to be 1. So we got to ask ourselves, okay, so when will x plus 4 equal 0? Well, x plus 4 will equal 0 when x is negative 4. Right? And so what this does to our graph, it's going to shift it over 4 units to the left. So now there's my point, and so now my curve is going to look like that. Right? And then if we did another one, if we did y equals 2 to the x minus 3, again, the question is when will that exponent be equal to 0? So we can take this part, set it equal to 0, and add 3. And so then now x is going to be positive 3. And so now this one shifts it to the right 3 units. And again, we get the same basic shape, just shifted over 3 units to the right. So we can move our shape in regards to either up or down and left or right. So, how about if I did one that combines the two of these together? So let's say we want to graph y equals 2 to the x minus 2 plus 5. Right? So we want to put that on a graph. Well, first off, the plus 5 is going to take the entire shape and move it up 5. And so it moves our asymptote line up 5. So we're going to have it here. Okay. And then x minus 2 will equal 0 when x is 2. So when x is 2, right, we go up 1 unit. Right? So 2, 1. And so we're going to get a graph that looks something like that. Right? So we combine the two things together. Move it up and down. All right. So that in terms of our basic exponential graph. Right? Well, in terms of exponential equations, you can get the equation for compound interest. So a sub t is equal to a 1 plus r over k to the k. So in this equation, this is the amount at time t. A here is the initial amount, so how much money did you initially put in the account? Okay. R is the rate, so the interest rate. K is the number of times compounded. So, for example, if it's monthly, that would be 12. If it's quarterly, that would be 4. If it's semi-annually, that would be 2. If it was just annually, that would be 1. And if you did daily, that would be 365. And then T is the time frame in years. So we have in terms of what everything stands for here, right? So, for example, then you get a question that looks something like this. So, you have how much money? So, how much money would be in an account if $5,000 is deposited at 2.5% APR. Compounded monthly for 5 years. Right? So first you want to do is write out our equation, plugging in all the appropriate numbers, and so A sub t, you'll be 5 years, is going to be 5,000. 1 plus, our rate is 2.5%, which as a decimal will be 0.025. Compounded monthly, so that is going to be 12. Our exponent, well, it's compounded monthly, so 12 times for 5 years. And so our exponent, which was kt, is going to be 12 times 5. So our exponent here is going to be 60. So then it's a matter of plugging that all into the toy and getting the number. And so we would end up here, we get $5,665.01. Given that we're talking money, we'd round that number to the nearest penny. So we have in terms of our compounding. Well, in terms of our exponential, we get in terms of what's called the general form. So y equals a b to the x. So for example, we could have y equals 0.01 times 2 to the 30th. So we get in terms of something like that. So we want to be able to, can we come up with an equation then, given we know some information about what's going on? So we want to determine the equation. In the form of y equals a b dx. Right? And we got 2 points. We have this point, 1, 4, and we have the point 3. Right? So we want to figure this out, all right, in terms of this. All right? So we know that in terms of we have x and y, right? In terms of what we have here. Right? So if I look in terms of my first numbers here, we would have, this will give us 4 equals a b to the first, which of course would just be 4 equals a b. Right? And if I do the same thing with my second set of numbers, we would have that 20 equals a b cubed. Right? Right? Well, we need to figure out what the A and B are, right? Well, from my first equation, we can solve either for A or B. And so let's solve this for A. And so if I divide by B, we got that 4 over B is equal to A. Right? So we have in terms of, right? So we can take this now, we're going to take this part, and we're going to substitute it in here for A. Right? So we're going to do that substitution. So we're going to have 20 equals 4 over B times B cubed. Right? And so now we're going to take this equation and solve this for B. So this is going to be 20 equals B cubed divided by B is going to give us B squared. Right? Right? And so now we can solve for B. So we're going to divide by 4. And so 20 over 4 is 5 equals B squared. And then the opposite of squaring the number is to find the square root, and so B is going to equal the square root of 5. Right? And so then A is going to be 4 over the square root of 5. Right? So we get in terms of that. Right? I think about this is, technically, you're not supposed to have radicals in the denominator, so we would have to rationalize our denominator. And I can do that by multiplying top and bottom by the square root of 5. And so we get 4 square root of 5 over 5. And so now we can write our equation out, and that y is going to be 4 square root of 5 over 5 times the square root of 5 to the, that would be the equation that goes with those 2 points. So in terms of exponential growth, so we had to start this, I had that equation dealing with world population growth. And so we look in terms of that equation. And so that equation was in this form. A sub t equals A naught e to the k t. Right? So again, A sub t is the amount at time t. A naught is the initial amount, how many did we start with? Okay. K is the rate of growth, which would then be a positive number, and if we're talking about rate of decay, this would be a negative number. And then T is the So given a question that deals with this, right? So given something like this, given an initial amount of 100 grams, decays to 20 grams, decays to 70 grams, to 70 grams in after 20 hours. to know how much would be left after $100. So let's write down what we know. We know that A naught, what we started with, is 100 grams. Right? So A naught equals 100 grams. Right? We know that A sub 20 is 70 grams. And what we want to find is A sub 100. Is what we want to get, right? Yeah. Well, we don't know the grade, but we can figure it out because from these two numbers, set of numbers, we can figure out the value of K. Right? And so we have our equation was in this form: A sub T equals A naught E to the KT. Right? And so we can use these set of numbers to get the K value, and then once we got the K value, we can answer the question of what we want. So let's plug in what we got. And so we got 70 is going to equal 100 E to the 20 K. And we want to solve this now for K. So the opposite of multiplying is to divide. So we'll divide by 100. And so we get that 0.7 equals E to the 20K. Now it ends up that the opposite of natural of E is to find the natural log. And so we're going to do the natural log of both sides. And so we get that the natural log of 0.7 is going to equal 20K. So natural log and E cancel each other out. And then the next step would be to divide by 20. And so we get that the K value here. So we're going to have the natural log of 0.7 divided by 20 is equal to K. And that comes out to be approximately negative 0.0178. Well, now that we know what the K is, we can answer our question, which is how much will be left after the time frame. Right? And so A sub 100 is going to equal our initial amount, which was 100 E to the negative 0.0178 times 100. And so it ends up after 100 hours, we would have 16.86 grams of stuff. So again, natural log and E are opposites of each other. So for example, if you tried to do this on your calculator, and I gave you something like this, and I said, okay, what is the natural log of E to the 5th? You plug that in on the toy, you would end up, this comes up to be 5. As you ask, what is the natural log of E to the 112th? This will come out to be 112. So natural log and E cancel each other out. So we had in terms of compound interest equation, which we had up earlier. We can also have in terms of what is called continuous compounding. given by A equals P E R T. So A again is the amount. How much money you got? Amount. Again. So the amount of money you have in the account. This is the principal. How much money did you put into the account? R is the rate. And then T is the time. And again, this would be in terms of years. Right? So, for example, let's say we now did like the question we had earlier, and we did that P was $5,000. R was 2.5%. And T was 5 years. How much money now would you have in the account if you did continuous compounding? And so A would be 5,000 E to the 0.025 times 5, and you find out now you would have $5,665.74, given that we do continuous compounding, right? And so you find out it's slightly different than what we had earlier. It's you can remember from our previous, we said when we did the other compounding, it was 5665.01. So you made a few more cents doing continuous compounding. And lastly, we then, like we did earlier, look in terms of end behavior of our equation. And so, for example, we have this, y equals 2 to the x plus 3, and I want to know what's the end behavior. So as x goes to infinity, and as x goes to negative infinity. Well, as x goes to infinity, this takes off to infinity, right? As x goes to negative infinity, well, if this is going to be 2 to the negative whatever, this number is basically going towards 0, and so the end behavior will be this is going to be going to 3. Right? So we have in terms of just a little bit more about logs and natural logs. Okay? And so what do they tell you? And so, as we had up earlier, if I do the natural log of e to the 7th, this will give us 7. And if I did e to the natural log of 5, well, then this will give 5. So the natural log and e cancel each other out. Right? Other logarithms, there's log base 10. So the log of 10 will end up giving you 1. If you do the log of 100, this will give you 2. If you do the log of 1,000, you'll end up that this will give us 3. And so really what we ask the calculator to find is 10 to what power is 10? And that's 1. 10 to what power is 100? 10 squared is 100. And then 10 to what power is 1,000? And that would be 3. And so if I did the log of 10 to the 8, we would end up that this would be 8. Right? If I did log base 7 of 7, so if these two numbers agree, then it'll be 1. And so you can do log of other numbers besides 10 and e. Let's see, other things we could look at would be in terms of something like this one. If I said, okay, what is the log base 3 of the square root of 3, right? Well, square roots can be written in terms of exponents, and so this would be the same thing as saying log base 3 of 3 to the 1/2 which means we end up with just 1/2 for our answer. Right? I could also ask in terms of given something like this, what is the log base 9 sorry, down one. No. But, yep. So given something like this, I want to be able to rewrite this in terms of an exponent. And so when I do that, of the x, you have that this number, the exponent number goes to the top, and then the root number will go to the bottom. And so this would be the same thing as x to the 9/4. And so now, if I do an example where we have something like that, and so if I want to do what is the log base 9 of so something in terms of this, and I want to do this, we would end up, this would be log base 9 of 9 to the 5/8, and so we end up here that this is just going to be 5/8, right? And that will conclude this lecture.